Hi everyone. So now we discuss linear models. That means multiple linear regression models. So think about multiple predictors x1 to xp. So these are variables. For example, x1 is percentage that people voted for Gore, and x2 may be percentage of African American. And let y be response variable. So y is a variable that we want to explain. For example, y is the undercount percentage. Then multiple linear regression assumes that y is equal to linear combination of beta naught to, x1 to xp plus error epsilon. So here, the epsilon are traditionally assumed to be IID. So IID means independent and identically distributed. For example, to explain independence, we think about randomly picking up one student from each grade from an elementary school. Then we make them to take the math exam. Then scores for 5 students from grade 1 to grade 5 are independent as long as those students are selected randomly. But those students' score are expected to be different because 5th grader is better than 1st grader. So in that sense, each students have different expectation, different distribution of scores before observing. So it's not identically distributed. So in this example, errors are, so the observations are independent but not identically distributed. On the other hand, think about the temperature at noon in Singapore in each day. Then Singapore is on the equator, so temperature distribution of different days are almost identical given no information. So we have the same expectation on temperature on January 1st and July 1st and so on. In that case, the temperature at noon in Singapore in the next year from January 1st to December 31st are identically distributed, we can assume. But those are not independent because if hurricane comes, then temperature will be lower than usual for several days. So in that sense, those observations are not independent. So you can see that independent and identically distributedness are different concepts. And usually we assume expectation of epsilon is 0 because we want to think about epsilon as an error. If expectation is not 0, we can just incorporate that part in beta naught. Later, we drop these conditions such as independence and identically distributedness. But for now, we assume these are independent and identically distributed. Okay, so suppose that there are n observations, for example, 159 counties in the dataset, and yj be the value of y for the jth observation. So undercount percentage for each county. So we have y1 to y sub 159. And xij be the jth observation for the ith variable. So we observe, for example, percentage of African American for each county. So represents county. Sorry, the I represents the variable, the percentage of African American, and the J represents the county. J is equal to 1 to 159. Then this equation 1 is written as equation 2. So equation 1 is a general form, but for each observation J, you can explain that Yj is equal to a linear combination of x1 to xp plus epsilon j. And here, the beta naught, beta 1, beta 2, these coefficients does not depend on j, so it's common. Okay, so in terms of the probability theory, we assume that, for now, we assume that the beta naught to beta p are constants. So because this is a kind of unknown truth, but we assume that such constant exists. So this is a constant, these are constants, and x1 to xp. So these are predictors, and we assume that these are deterministic. So again, this is not random, but constants. And epsilon and y are random. So epsilon is an error. So you can imagine that we assume that is random. So basically x and y have some relationship, but the individual case have some error. So epsilon is random. If epsilon is random, so on the right-hand side, the first p plus 1 terms are constant, but last term is random variable. So left-hand side is also random. So epsilon and y are random variables. So these are probabilistic structure. In terms of data, x and y are observed because these are variables. And beta naught to beta p are unknown truths. And epsilon j cannot be known unless beta naught to beta p are known. So that means only x and y are observed and others are not observed. And often we have additional assumption on epsilon, such as epsilon has distribution normal 0 sigma square. So yeah, here sigma is the standard deviation of epsilon, and which is unknown. So this is the basic structure of multiple linear regression. So now we have an example. So this is Georgia voting data. And suppose that we want to explain undercount by percentage for war and percentage of African American. So we want to explain why by x1 and x2. So basically we have to focus on this figure and this figure. Those two figures have correlation coefficient of about 0.2. So we have positive association. So you can imagine that maybe trend line is around here and around here, but it's not clear because correlation coefficients are small. So now we fit this model. Undercount is equal to beta naught plus beta 1 percentage Gore plus beta 2 percentage African American plus epsilon. In R, it can be coded as this: the LM undercount tilde the percentage Gore plus percentage AA plus data is equal to something. So this is G is the entire data frame, the Georgia GA vote data set. If you have more than 2 predictors, you can connect everything by plus. So you can put plus x3 and so on. Then this is the output of this LM function. At first, we name it as L mod. Then we typed summary of L mod. Then this output appears. And basically beta naught, beta 1, beta 2 appears here. Of course, this is estimated by this 159 observations. So we don't really know the true beta naught, beta 1, beta 2, but these are estimate of beta naught, beta 1, and beta 2. So usually for estimates, we use hat symbol. So hat means this is not genuine one, true one, but this is an estimated quantity. We explain other outputs later. So this is basics of multiple linear regression model.